you can all hear us and that we're coming through loud and clear from deepest, darkest remote Lancashire. It's a very, very simple presentation, and quite a bit of this I've done before. But I thought, I've given a few of the conversations that I've had recently with our membership, I've subtly changed the emphasis on this to try and cover some areas where we think there's some concern, some areas where there's maybe scope for some change, and some areas where I'd just like to check and sense check what we as a trade association are thinking about going forwards. Peter, I'm hoping that you can hear me and I'm coming through loud and clear. Right. Okay. So the usual agenda, why do we need it? Where do we find rules and regulations behind it? And sources of guidance. Okay. So many of you have seen this before. It comes from why do we need to consider structural fire protection? You've got there in the top corner of the screen the actual Building Act, and the Building Act says the building shall be designed and constructed so that in the event of a fire, stability will be maintained for a reasonable period. Okay, well, what does that mean? And why is that a problem? Well, why it's a problem is the fact that we know that concrete will spoil, we know that timber will char, and we know that steel will soften and weaken. And that picture bottom left is a classic example. So we've got there two steel beams that have got so hot that they've not been even able to support their own weight, and they've softened to the extent and they've deformed. There's a wooden beam going across there which has charred and degraded, but is actually still strong enough to even support the steel, and the steel sat there on it. Okay, so we know that these things will happen. What does a reasonable time mean? Where does a reasonable time come from? And within building regulations, within building codes, you will find specific provisions that what a structural frame needs. This is B3, B4 out of ADB for England and Wales, but there are similar provisions, similar tables in Scottish Technical Handbook, within the Northern Ireland Technical Booklet, and even in the Republic of Ireland in Irish Technical Guidance Document B. And there are these similar tables that tell you what the structural frame needs, and it needs a certain amount of load-bearing resistance, either to the European standard or to the old historic BS 476 tests. And the period of fire resistance are determined by building size and building use. And you see that here in terms of table B4 that you see below. Right. So timber. Well, we know timber will char. And it chars typically in fires at temperatures above 350 degrees C, and there's a rate of between 0.6 of a millimeter to 0.8 of a millimeter, dependent upon the type of timber, the type of wood that the actual timber members are made out of. And there's a very simple approach here. You over design the amount of structural timber with what's called sacrificial material. In the event of a fire, the sacrificial material is charred, and it's dead simple. If you had a softwood that chars at a known rate of around about 0.8 millimeters per minute, and you want 60 minutes structural resistance, you make sure that the member is over specified to the tune of 48 millimeters all round, and then you've dealt with the softwood, you've dealt with your fire protection, and that's how it works. And that's a really simple process. Okay, structural steel, well, we know it won't burn, unlike the timber, so we haven't got any reaction to fire issues, but it does soften, as we've said. And I use this, this is chemists treading all over engineering world, saying, imagine a beam supporting a load of 1 ton, and we design it to give more tolerance than it needs because of structural design. So we design it to cope with, be able to carry 2 tons. And the failure will happen when this beam hits 550 degrees C, and there's meant to be a graph appears, and it's there. The graph is there. Slides have got out of order, and the graph is here. So we see that on the graph there, 50% steel strength. When the steel strength reduces down to about 50%, 550 degrees, and you plot across, plot down, That's around about 550 degrees C. Okay. Concrete, well, concrete like steel doesn't burn, but it's a complex material and there's lots of different factors within the makeup of the concrete that can affect its fire resistance performance. It basically what the concrete is doing in bending mode like this is providing insulation to steel reinforcing bars. And one of the problems occurs if the concrete spalls and the reinforcing bars become exposed. And you see here a concrete beam that's been fire tested, and the concrete's spalled off, and the steel rear bar has become exposed to the fire, and that's going to cause early softening and help bring the bending around. So it's how much insulation you're providing to the rebar reinforcing, and that's going to be of interest in that particular case. Okay. Now, main fire resistance test method, we use the European classification system, and the UK government tends to be moving more towards the European classification system, BSEN 13501 Part 2, with that letter R indicating load-bearing resistance. And there are all sorts of tests within the 13381 series. Part 3 covers concrete sections and concrete slabs. Part 4 covers passive fire protection for steel, boards, slabs, mineral wool, etc. Part 7 covers timber protection, and Part 8 covers reactive, so intumescent coatings, reactive systems for steel. And these are testing for products to improve the structural fire resistance of the relevant substrate, and how those products tested and are quoted and assessed varies subtly differently. They all have the assessment methods within the test method and what they're quoted. And so, for instance, with the concrete test and the steel test and the timber test, rather, concrete and timber, you get a level that sort of gives you an equivalent level of insulation as if you had concrete there or timber there, more concrete there or more timber there. And then passive and reactive, you get the big tables, and I think there's one of those is going to appear at some point later in the presentation. Of course, BS 476 is still allowed in both UK and Irish building regulations and is commonly used. BS 476 Part 20 is a test method, but it doesn't have an assessment method. So the assessment methodology for structural steel, as for both reactive and passive systems, is written into the yellow book, and that's then used by the certification bodies to produce that. So if you go that way, you can claim load-bearing performance, but what you can't do is claim the European R classification. Okay, which brings me nicely and neatly to poll question 2. Here we go. So which testing code do you use? There's a single choice there. And which system should UK regulations use in future? And there's a single choice there. And up pops the answer. So the vast majority of people are using 476 and 13381. Very few using, some using mainly 476, very few using exclusively 476. Interesting, quite a few using exclusively 13381. So I think that's swinging more towards the 13381 way, and most people favouring that. We think we should move more towards 13381 in future. Okay, excellent. Thank you very much for that. Right. So at this point, I'm going to go off on a minor little tangent, and for which I apologise, but hopefully you'll see why in a second. So in last year, we started work in 2019, and last year in September 2020, ASFP worked with BESA, the Building Engineering Services Association, FIS, the Dry Lining Trade Association, BISRIA, and the Gypsum Product Development Association to come up with a best practice guide on designing and specifying fire stopping. So why did these trade associations come together? Well, we asked ourselves at the very start of the process, why fire stopping failures occurred. What was it that meant that fire stopping failures were occurring on site? And one of the reasons that we came up with as our primary reason was that fire stopping wasn't considered in enough detail, early enough, and well enough in the design process. So that quite often what would happen is that fire stopping, the fire stoppers would get to site. The design of the fire stops would be what's called contractor design portion of the contract, and the contractor would have to come to site and be faced with things that to fire stop where they couldn't design, and they had the design responsibility for stuff that had been built in a way that made it unstoppable, if you like. The contractor couldn't guarantee a successful outcome. So what we said, what this guide advocates, is talk more, talk earlier, and bring more people along to consider these aspects of fire stopping. Okay, so why have I put a slide on a fire stopping guide in a presentation on structural steel? Well, fire resistant materials are not commonly added to timber or concrete. Okay, so their design already covers fire resistance requirements, but we do within our ASFP TG groups, and within people who I talk to who are allied to those, both as installers and as manufacturers, we sometimes come across steel structures where the cold design's been done, but there's been no consideration of what's going on in fire, or maybe the fire design has been done. This is the more common thing, but the design information doesn't come down the contractual chain. And because the design information doesn't come down the contractual chain, we're left in a situation where you're trying to work out how to treat this structure, and you're struggling to work out what to do and how to do it. So we've got an issue with that, and of course. And so what I'm advocating here is the same message in the way for especially for structural steel as we have for the fire stopping thing. We need people at the design stage to talk more about structural fire protection and consider structural fire protection more and earlier in the contractual process, so that we don't get into this situation. Okay, and I suppose the question is, why is this relevant? Well, the design code historically in the UK has been BS 5950 Part 8. More recently, that's been moving towards the Eurocode, EN 1993-12. And we're in a situation where the vast majority of structures, I would imagine, nowadays are being designed to the Eurocode. One of the challenges is that the Eurocode can place more load on steel sections than the old BS 5950 loadings, which means that consequently there's going to be a lower critical temperature and therefore more PFP materials required. All right, and as well as that, design codes also define different building use types, and when working out how to interpret the design code, you need to consider the different building use types, because the different building use types can cause different failure temperatures. Okay, now this is get some tables here as we come up. So we have got yellow book tables, and the yellow book tables are repeated also in and out. If you want a shorter, he said shorter-ish version, there's some tables in a document that we've recently published, advisory note 24, and that gives the critical failure temperatures that we would believe you should use. And advisory note, so if we consider advisory note, the tables in advisory note 24, because there's been a couple of subtle changes. Okay, many of you will recognize the temperatures there under the office assignation, where a three-sided beam is failing at 620 degrees C, and an I-section column fails at 550, and a hollow column fails at 520. And that was traditionally how the industry has operated for many a year. Okay, But of course, that's relevant for an office, but it's not necessarily relevant for a storage stair or a lobby type building, again under 5950, or for any other structure under 5950. And so we've got various areas of temperatures there away from 620, 550, 520, where the use is making a subtle difference. If we look at the Eurocode, that's table 16 in the yellow book, and it's also within that. So there you go. And we've got here office, domestic, we've got congregational, shopping and car parks, and we've got storage or default where occupancy is not known. And you will notice the vast majority of those Eurocode temperatures are subtly lower than the BS 5950 temperatures that we saw on the previous slide. So for instance, the office now is down to is come down from 620 to 5 for three-sided beams, 620, 576. So those, there are some of those that are subtly higher, but the vast majority are lower. Okay, and so I would advise you, please, this is the area where you need to consider these temperatures. They're very dependent upon the design code. They're very dependent upon the use type, and therefore that sort of information needs to come down the contractual chain to make sure that structures are properly protected, and it doesn't always. So we put that document in. There's a flow chart in advisory note 24 that sort of explains this all and underpins this all. I'll let you can see that. Please have a look at that, and that's those temperatures and are in the tables that you've just seen on the two previous slides. Okay. Now, the alternate to all this is, of course, that you could get a fire engineer to take your structural model, run it through some fancy piece of software, and calculate the failure temperatures. I'm just going to advise you make sure that this is properly done, because we can see those failure temperatures from that table 16 for the Eurocode. There's nothing on there. The highest one on there is 603 degrees C. And if you get somebody that comes along and says, that's fine, we could go all above 650, your structure has been designed in such a way that that's possible. There's a level of restraint. There's a level of conservatism in the steel design. Please make sure that any such thing has been properly done by a competent engineer. If you see a high temperature above 600, 650 and above, ask the question. Just make sure that that's been done. There's an advisory note out there, advisory note 19, that considers the use of elevated critical steel temperatures. Just consider and make sure that it's been done properly. Which brings me neatly to poll question 3. I'm hoping, there you go. So this is again is a single choice question, please, folks, and this is one where I'm asking you to help us and sense check what we think we're going to do in future. What do you think we should adopt as a policy for structural steel limiting temperatures? Obviously, in the past we had 620 and 550 as at the 520. We've now got this system that's considers the two design codes. It considers the two design codes, and it considers different usage types. So are we happy with that approach? Is that too complicated, and should we just have one simple default temperature for beams, for columns, for hollows? The option 3 there is the historical figures, or should we make sure that we're using an engineer to properly determine project specific values for every project? And I will let you mull over that one and think over that one for a few seconds. Here we go. And an interesting spread, 38%. The majority, although it's not a sort of a parliamentary majority, just you say 38% say, as we using the tables we've got, 12% think it's too complicated and we want one simple default for beams or columns, etc. 17% of you still want to use 550, 620. And unfortunately, to that 17%, I would say that we can't go there without fundamentally changing all the steel design codes and the national annexes that underpin Eurocode. And that's an awful lot of stuff to do. So that was put in there deliberately to say, you know, I'm sorry, folks, I don't think we can get to that. And 33% of you say we should allow an engineer to determine project specific values. Okay, right. Thank you very much. We're going to crash on with the rest of this now. So it says hopefully done. There we go. What should I consider when specifying structural steel protection? Well, obviously, I would, as ASFP, we always talk about third-party certification is the way of the future, and we'll explain that a bit more in a few slides' time. We've already covered where fire resistance period comes from. We've covered design codes and the effect that can happen, and how design code can influence failure temperature. And is it a default failure temperature based on the design code, or are we calculating one? The certification standard, BS and Yellow Book or EN or something else, you know, and bear in mind, it says the Building Act says do it reasonably. And if the man in the white wig says, well, how have you done it reasonably? Well, I've chosen a different standard. Like, okay, fair enough. It's your decision. Make sure it is a reasonable one, and make sure you've done the due diligence if that's where you go. Okay. Section size, section factor, emissivity, and type and orientation are left to consider, as are the environment and project specific testing. So we'll just quickly canter through that last little bit. I'm sure many of you on the call have already seen this, but here we go. Section factor and emissivity. You know, slender steel will heat up faster than a chunkier section. So we have this thing called HP over A. More recently been rebranded in European world as V over A. And we've got, it explains how to the Yellow Book will explain to you how to calculate what the heated perimeter is, what the cross-sectional area is, and basically a high HP over A will be a slenderer section that will heat up faster and will therefore need more fire protection applied to it than something that's a lower HP over A. And then beyond that, for I sections and passive systems, you can see that the different shapes and the different things go forwards, different shapes and different ways of treating them. Okay, and that has an effect on the heated perimeter and therefore on the section factor, depends upon when you're using an open profile or a box profile. If you're using a standard roll section, that there's the tables in the Yellow Book that explain what the section factors are for all the different steel sizes of steel. So there's lots of information in there that explain all that. And there's a real big confusion for orientation. Major potential, three-sided beam loadings, they always need a concrete slab. You have to treat hollow sections separately. And there's a thing called ASFP's Advisory Note 12, which we jointly published with the British Coatings Federation, which is a best practice guide for how you specify reactive coatings. But that covers that covers some of the passive stuff as well when you're looking at how you would expect, how you would understand steel sections. So again, you can find all these information off the ASFP website. Floor construction has an effect. Do you need to fill, are there voids above the steel beam in the metal deck? And one of our members very kindly put some presentations on this and slides together, which I've borrowed. Thanks, Bob. So this is how to treat voids between metal deck and top flange of beam. And Yellow Book table 20 has advice that it explains where you need to fill voids or where you don't fill the voids, and how you compensate for that accordingly. Cellular beams are increasingly used, which behave very differently in fire because their mechanical failure is different. And I've got beam services running through the web openings, and I see a question. I'm just asking. I was just starting to move on to this, and I see a question has popped up, so we'll deal with that. We'll deal with that later. In fact, the question that's been posed is about 3 slides time. So here we have this issue where the services are passing through the openings, but the problem is that, of course, the structural steel is going to behave very different. Veer and deal bending, web post buckling, all sorts of different fancy structural failure modes. And so we have a special series of testing with using a cell beam protocol in the yellow boot, which is now basically been repeated and sorted in BSEN 13381 Part 9. And we've got an advisory note 11 that explains cell beam testing, and we do run a register of tested products to explain this in further detail. Many manufacturers now provide IT solutions which can perform lots of different things, from a simple lookup function to work out how much fire protection you need on a piece of steel, to do more complex calculations, looking at failure temperature based on structural assumptions and cell beam analysis. And there are even those out there that link to your CAD model to extract the steel frame information and post the PFP loadings back into the model. And there's even at least one system out there, if not more, that will actually look at your coating and your steel thickness and optimize it for cost or ease of construction. And so that's the sort of thing that's being discussed, and I'm sure this is an area where we'll continue to see developments and interesting things going forwards. I've put this one up in the past. I'm going to subtly change what I say about this one going forwards. This is a very, very generic table for intumescent coating, saying what is possible in terms of environmental impact, the environment and lifetime for steel protection. And what you will see is that different products, and this is a generic sort of thing. I say that, so you must consult product data, because some water-based it's possible to make them more durable. It's possible to make solvents-based more durable and or less durable than is implied here. But what tends to happen is that a water-based will do provide less durability in harsher environments than a solvent-based, and the epoxy systems will provide most durability. And there are some new novel systems that sit somewhere between solvent-based and epoxy coming to the market. But the thing I would mention here, which maybe is something we haven't mentioned before, which is, remember to consider the construction phase as well as the final use phase, because what's happening is the construction phase often is the most onerous thing. So you've got an office building that's going to be internal air conditioned for life of building, that's fine. But if that steel frame is going to sit open to the elements as a construction site for 6 months, 12 months, while the office is being built around it, that is a much more onerous environment than the rest of the building's lifetime. So please consider construction phase as well as final use, because it's an area we see things that may be causing issues going forwards. Okay, a bit of an ASFP plug. Lots of information on the ASFP website, series of technical guidance documents. A lot of these are the documents that have been around for a while, but they're still just as valid today, and still TGD 11, TGD 16 are still used to this day as the de facto code of practice. There's some interesting information in 8 and 13 as well. We've also got a lot of advisory documents, and the list of advisory documents continues to grow. We last did a presentation on structural steel last year, and since when 21, 23, and 24 have come out and been published, and so that's there's lots of other advisory and stuff going forward. Right. So this is one of the things, of course, within ASFP, we talk about why do we need certification of products? And one of the key things we see going forwards is the fact that there are three ways that people can make products available in the marketplace: self-declaration of performance, a test report, and third-party certification. And if you consider the self-declaration thing, you know, if I tell you that my product's been tested to, or worse still, it's been designed to, or it complies with, there's no guarantee that that product's reached the correct standards. So was it tested? Was it impartial? I don't know. And so we're uncertain. There's a bit of risk there. I have a test report. Okay. So if I have a test report, the product's been tested, but it's only a snapshot in performance. And some people will take a test report and say it's a certificate when it's just a test report and a snapshot of evidence. And so obviously that brings you to the question: is the test sample representative of what's being produced today? Have there been changes to the design, to the materials that are used? And therefore you still have a level of risk. But third-party certification, not only does that come with demonstrate the product's conformity, but there are ongoing audits to the company's production, the company's manufacturer's product going forwards. And so that ensures that the product is the same specification and design as that tested and has the same performance as that tested. And so that's the only route to confidence. Now, third-party product certification is the de facto standard going forwards. But sometimes you do get elements that are outside the scope of testing, and this is one that I've shown before. It's a really nice example because those main cross beams are triangular shaped concrete filled sections that were nothing like anything that had gone before. So what we did when we were looking at those was there were a series of mock-ups produced, and manufacturers tested their product on the mock-up that was produced, and then that product, which was already third-party certification, were tested by a third party to show that because they're outside the scope of the test standards. They are completely different, and so that's a usable thing going forwards. Okay. We also get to the issue that it's not uncommon to see different systems used on one product. We see there we've got some sections with intumescent coatings that have been then boarded in. We've got a board interfacing with a passive bat system there, and so we've got there's many possible reasons for this. And TGD8 gives advice on how to do it, and that's usually with a butt jointed connection, but not with patch, and it's really not advised to patch these systems together and in sort of like face or small areas. It's really not. And I mention that because that's a question that's come into us a lot of late, where people are going back into buildings and looking historically to say, what have I got? What am I going to do? How do I repair this and sort this breakdown out? Framing beams and columns, and we've mentioned that there's an advisory note on this at the moment, and technical guidance document 13. So intumescent coated steels often meet load bearing walls, and obviously intumescent steel gives you the load bearing requirement, but it doesn't give you the integrity and insulation requirement that you see of separating elements. So at the moment we've got cladding in is possible. We need 50 mil gap and care to care regarding the touch area, how much of the intumescent is being touched to prevent the restriction of the intumescent. And we've got a research project underway between ASFP and British Coatings Federation to produce some better guidance on this and how this all unfolds going forwards. And it can get even more complicated. And there was a picture I came across recently, and I've tried to go back and find it. So here we've got a cell beam, and we know that cell beams they could well be tested to BSEN 13381 Part 8, which is the plain steel test, 13381 Part 9 for load bearing capacity. And so we've got that issue there. Okay. So that gives us our structural fire resistance. Now imagine that cell beam with those ducts and pipes and cables passing through it is sat on a compartment line. And the compartment line would be tested to BSEN 1364 Part 1 for integrity and insulation, which is subtly different to the load bearing capacity of the steel beam. And then we're penetrating it with ducts and dampers and cables and pipes. And a fire resisting duct would be tested to BSEN 1366 Part 1. And again, that is integrity and insulation. And the cables and pipes, if there were cables and pipes passing through, so there's insulated pipes on there, they're tested to BSEN 1366 Part 3, integrity and insulation. And it's at that point that we've got the challenge, because the building is a series of these things coming together, and that we've got to model how all those systems interact and work with one another. And at the moment, there's no test standard for that brings all these things together. And given the number of infinite combinations of these things, you couldn't do it within a standard. So we end up within a situation where the only way to reconcile these at the moment is to conduct some form of technical evaluation, okay? Looking at structural configurations and interfaces and considering how the beam affects the petition affects the beam, how the penetrating element affects the petition and the beam. And those are the only way that you could do that is to get somebody who's skilled in that to do that. Advisory note 17 explains how that works and how it will work, and the fact that it gives you a sort of a steer to people conducting these technical evaluations in lieu of test on how you would do it and how it would be done. And that's underpinned by a document called the Passive Fire Protection Forum's Guide to Undertaking Assessments in lieu of fire testing. And so those two documents would explain why we need to be allowed to keep the ability to conduct these sorts of assessments, and what they and how you should do it, and to a certain extent who should do it. Okay, which brings me latterly to poll question 4. So whose responsibility should it be to sign off the interfaces between construction systems? Okay. Oh, that says single choice, and I didn't think I wanted that one to be a single choice. I apologize for that one. I thought that, but let's see what people say. And here we go. So it's split between architect, designer, and fire consultant, with some being going to the installer and then small quantity to the manufacturer and system owner. It's quite interesting because an awful lot of them at the moment actually do more sit with either the manufacturer, installer, and the system owner, or the installer. And what I would say is that what it actually needs, the outcome, that what you actually need is all of those people to work together to mitigate the risk, because the manufacturing system owner knows how their systems are going to perform and as it should be involved in the process. The installer knows what he's building and should be involved in the process. But equally, by involving the architect and designer in planning these interfaces better at the start and getting the fire consultant to head this all up, then that's the way that ensures that you're managing these risks rather than just trying to divest them and sort of get rid of them and be shut of it. Thank you very much. Right, the good news is we're not far away from finishing, and then we can get on to looking at some of the questions. Okay, so just mention a brief mention of third-party certification. We've already mentioned that third-party certification for manufacturers and what the benefits are. We would also recommend, for ASFP installer members, third-party certification is a mandatory part of their membership, and it has been for 20 years. We would always recommend the use of third-party certificated products for passive fire protection, and we recommend the use of third-party certificated contractors to install it. And there are a number of different certification bodies who are members of ASFP who run schemes that cover certification of both products and installers. So in summary, what I'd like to say is basically the message I've been trying to cover within this presentation is that we need a greater focus on design code and building usage through the contractual chain. Okay, and we need to plan and design the interfaces better, and we need to think about how the environment in construction phase as well as the environment in long-term use to help ensure, and all of these steps could help ensure better passive fire better conducting of our passive fire protection works. Okay, but in final summary, and you've again seen this before, PFP for structural steel and indeed any structure is a complicated subject. For best chance of success, always specify third-party certified products installed by third-party certified installers, and there's lots of information out there on the ASFP website to help you come up with stuff. Which brings us nicely and neatly at 12:45 perfectly to the questions and answers, and hopefully Mike's going to appear on the screen in front of me.
And here I am. Thanks, Andy. I hope everyone can hear me better. I switched microphones earlier on. So we have a few questions. I'll go through the Q&A first. Some are shorter and more concise. Some are a bit more convoluted and a bit longer, but we'll go there. So first we have a question from Dan Martin. He said a recent project has had an increase from 60 minutes to 120 minutes. However, it has been identified that HS, I'm assuming, is that high tensile steel in terms of a beam?
I guess so, yes.
Okay. Cannot have a thin film intumescent coating applied to meet 120 minutes. How could HS meet 120 minutes? Hollow section, I think, is I've just seen a note, quick note flash up. So how can it be? So how can that be effectively turned from 60 into 120 minutes?
So I identified the hollow section cannot have thin film intumescent coating applied to meet 120 minutes. I'm trying to work out why the hollow section couldn't have thin film intumescent coating applied to meet 120 minutes. There are products out there with scope for intumescent coatings out there with scope that do 2-hour hollow sections down to about a 3mm wall. So I'm assuming if it's either it's slenderer than that, or not. As per installer information, apparently, I would suggest maybe look at other products, because I can think of some products out there with significant 2-hour structural hollow section scope, unless it's loaded to some particular factor that means you've got a really low critical temperature. But I'm sure there are ways of doing it. There are systems out there that can do stuff. So I'm at a bit of loss how to answer that one. Look for other products to discuss, I'm afraid.
Okay, and obviously, if you do find those, make sure they're correct tested and the correct.
You will find. Have a look on